uno che aveva definito una strength del soft XS.
Stanno tante definizioni, pure bianchi, pure gli ozzi lo nomino solo perché gli quindi una delle cose che
se lo mettete il soft XS?
sempre e comunque.
Sempre?
Non
c'è una slide. Dico quante ne trovo diversi indicativi.
Quante ne trovi?
Un po' meno del 60%
non ci credo.
Delle mie sorgenti.
Sono tipi 1?
No, tutto.
Vabbè, tipi 2
parlo di una
assorbiti.
Come?
Li dividi tra assorbiti e non assorbiti?
No.
Allora, è un po' tutto un cavolo per quello che mi interessa. Però sarà sempre bello ascoltarli.
Com'è che qui è sensibile o c'è un trucco per quando fanno le slide? Avanti questo. Ah, quindi è sensibile quando la gente usa questo qua. Non lo so cosa combinano, ma se lo pigiano tipo una volta e non vedono, gira, lo pigiano 10 volte.
Okay, take your seat, please. We are about to start. Come? Che è successo? Porca.
Dovrei starci nel tempo. Se non ci sto, il segnale qual è?
3 minuti di solito. 3 minuti. Aspetta. Non abbiamo lo schermo però.
E dov'è il ce l'hai il numero di...
No, perché alla fine ce l'aveva beta, io non l'ho mai preso.
Guarda se l'ho già fatto io, spento lo scherzo.
Ah no. Aspetta. Ma si è spento ora?
Sono tornato via, l'ha spento. Bene, veniva riacceso alla fine della pausa.
Eccolo. No. Ho mandato appena un messaggio. Aspetta, lo chiamo direttamente.
Qui siete, sì. Anche là.
Ah no, guarda. Dove l'hai preso? Qui dal fondo, che era quello lì.
Fondo, sì, sul...
Sì.
Allora vado, si deve andare a fare.
Vai. Questo però non serve perché questo è di quelli là. Quindi questo è il suo. Vai.
Okay, so the first talk by Alessandro Peca, X-ray spectral analysis of the 31.3 square degree stripe 82X, AGN properties and cosmic evolution.
Good afternoon, and first of all, I will spend 30 seconds to say that I'm really happy to be here, so I thank the organizers, and for some reason, this is my second AGN meeting, and I don't know, for some reason I like it, I like the spirit, I like the fact that we talk about science together, and it is very stimulating. So now I'm going to talk about my current project, the X-ray spectral analysis of the stripe 82X, and I'm going to show you some AGN properties and a little bit of cosmic evolution. A very brief introduction. So this is a projection image of the whole universe, and each point here is an AGN. And if you see that red stripe, this is the stripe 82, which is very nice multi-wavelength survey, and if you check the X-ray coverage, which is called stripe 82X, you can see that we have both archival XMM enchant observations and also XMM proprietary observations. And the overall area is around 31 square degrees. So a little bit of context. Why we are studying another X-ray survey? Well, here I selected two plots from two famous works on X-ray surveys, and you can see that if you go at high redshift and high luminosity, the number of sources decreases dramatically. And here on the right, you can see redshift 3 to 4 X-ray luminosity function, and you can see that it is constrained up to very high X-ray luminosity, but you can see pretty large error bars, and this is because the number of sources is very low. So what we want to do is to study AGN in this high luminosity and high redshift regimes. So these sources are very rare. So I know that this slide can be a little bit boring, but statistics is important. And stripe 82X is a very large survey, which means that the exposure time is not too much. This means that we have to deal with a very low count photon statistics. So in that case, we need to test what is the minimum number of counts to get a reliable fit. And to check it, we did MCMC simulations as a function of redshift, physical parameters, but also telescopes and models. And here you can see an example. This is for a simple power law model. Here you can see different telescopes, but also you can see that the thresholds that we put on net counts as a function of redshift vary also if you play with the physical parameters. So we did this count, this cut in threshold, and also if you want a very detailed X-ray spectral analysis, well, you need to take only solid redshifts. So we took only spectroscopic and high-quality photometric redshift. And at the end of the story, we selected around 3,000 objects. So if I remember well, I missed a slide. Sorry about that. So again, why stripe 82X? So as I told you, stripe 82X is large. Here you can see some surveys from 1920 as a function of area and hard band X-ray luminosity. And you can see that stripe 82X is one of the largest surveys so far in the hard X-ray band. So stripe 82X is also nice because our redshift completeness is close to 100%, and more than a half of the redshifts are spectroscopic, but also the spectroscopic campaign is still going on, so this number is going to increase. Also, we have a very huge multi-wavelength coverage, which means that we have also high-quality photometric redshifts. So we have also numbers. We have more than 6,000 X-ray sources, and 1,500 are hard band detected, which is always good if you want to study obscuration. So let's skip this. let's talk about some results. So if we have enough counts, we fitted all the sources with different models. So we wanted to take into account the main features in the X-ray spectra, so we use simple power laws, double power laws to take into account the soft excess, and then on both of them, we added reflection. And this pie chart tells you our results. So here you can see that for 80% of the sources, the statistics methods that we use, 30% of them prefer a reflection component, which is to say, even if you are working with low counts photon statistics, a simple power law is not always the best solution. And then we can make some typical distribution of an X, intrinsic luminosity, and then photon index, which are pretty consistent to what we can find in the literature. Then we can do, again, usually when you read a paper on X-ray surveys, you can see this kind of plot, redshift versus the hard band intrinsic, the observed luminosity. And here I put the NH in color code. But the first time that I did this plot, I was like, well, this is nice, we are happy about it, but how many AGN are we missing because of observational biases? When then we started performing simulation to try to understand something about that. And here you have the general scheme that we use. So we perform cubes of fake sources as a function of physical parameters like NH, which is the absorption column density, LX, and redshift. And then we convolved these cubes with all the observational biases. The result is a distribution like this one, which tells us the percentage of sources that we are missing due to observational biases as a function of redshift, NH, and LX. So what we can do with this kind of distribution is to correct our observed distribution and derive something that is intrinsic. And the nice thing of this process is that we didn't assume any luminosity function. So here we are just correcting for what we are seeing without too many assumptions. Then we were interested in the obscured fraction evolution. So these are the fraction of obscured AGN, only Compton thin AGN, as a function of redshift for different luminosity bins. And as you can see, our results are pretty consistent with some models and some results that you can find in the literature. But we are particularly happy about this plot because, for example, here, these 2 points, a redshift between 3 and 4, and for this luminosity range, the models here are extrapolated or they are constrained with a very low number of counts. So this is important because we are putting observational constraints at high redshift and high luminosity. And here you can see basically the same plot, but this time you have the fraction of obscured AGN as a function of X-ray luminosity for different redshift bins. Again, we are consistent, and again, we are so happy about this plot for the reason that I explained before. Now, a little bit about the future. So the work is not done yet because we use the master catalog from La Massa 16, and we realized that since 2016 to 1 year ago, we have a lot of new available observations in both the Chandra, here in red, and XMM archives. So we did some math and realized that we can double the current number of AGN, so we can obtain a sample of more than 10,000 sources, but also because here you can see that there are some overlapping observations, then we can also improve the depth by a factor of 2. And this is important because, of course, this will improve our current results. For example, our obscured fraction distributions, reducing probably the error bars. And then this will allow us to explore even more high redshift, high luminosity, and hopefully also the Compton-thick regime. And by the way, we proposed an archival proposal, and this was approved, so we should be happy about that. And that's it. Thank you for the attention.
Thanks, Alessandro. So questions for Alessandro? Yeah, okay. Mine is very easy. I mean, what do you mean by select the best fitting model? So what is the criterion you use?
Mm-hmm. Okay, so if we have enough counts, then we fitted the sample of sources with all our models. Then we performed some statistical tests. We tried with a delta C stat criterion, with a big Bayesian information criterion, and then the archaic information criterion. And playing with all of them, we chose the AIC because it's less aggressive to complex models. For example, very briefly, if you check the results between a model with a free gamma and a frozen gamma, and you plot the distribution of your gammas based on the selection criterion, for example, delta C stat or big.
You plot the NH, sorry, no.
Gamma.
You freeze gamma and then...
Yeah, for example, you can check the result with a frozen gamma and then with a free gamma, okay? And if you get if the frozen gamma is 1.9 and you do a fit with a free gamma and you get a gamma like 2, if you use a delta C stat or a big criterion, it always prefers the model with the frozen parameter. So because of that, we choose the AIC criterion because it's less aggressive. Okay. But the results are consistent. Yeah.
Roberto, but we don't have the microphone. Okay, one question here. Sorry.
By the way, this is Sebastian. He's our mascot.
So I was quite surprised by the little difference in the count threshold between Chandra and XMM spectra to get a reliable fit. Is that because Stripe 82 has short exposures, and so if you do that exercise on longer, the background becomes...
yeah.
So that's the main reason.
Yeah, the main reason is the background, the difference in the background. And also we fitted all the spectra simultaneously, and I found out that when you fit XMM only and you fit PN, MOS1, and MOS2, for some reason you have more fluctuations, and so the results could be a little bit different.
So you choose only one camera?
No. We fitted simultaneously all the spectra. Okay. But if you compare a fit with only one Chandra spectrum with a fit with 3 XMM spectra, the fluctuation in 3 spectra can produce such results. But the main reason is the background.
So you never use Chandra and XMM joint?
Yes, I also did. If we have both telescopes, we did a simultaneous fit. And yeah.
Last question by Marcella.
Is it about Rosita?
It's not really a question. It's an advertisement again speaking about the high luminosity part and the population of redshift luminosity plane. I want to advertise again the Seyferts survey, where that contains about 20,000 AGN over 140 square degrees, and there are all the spectral properties released in the paper of Liu et al. And I think it's a very good data set to explore in terms of these kind of studies, including probably the fraction of obscured AGN.
Yeah, thank you. Yeah, maybe we can, but thank you.
Okay, thanks, Alessandro. I think we are in time, so I think we can move on. So the next talk is by Francesco. Thanks again, Alessandro. So the next talk is by Francesco Salvestrini, Unveiling Compton-thick AGN with NuStar and mid-IR. observation.
Good afternoon to everybody. I'm Francesco Salvestrini, a postdoc here in Arcetri. I want to thank the organizer for giving me the opportunity to present my work. And today I will talk about unveiling compton-T AGN using NuSTAR and mid-infrared observations. As pointed out by Ivan in the first talk of this conference and also by Alessandro in the previous talk, when we talk about the AGN population, maybe we are missing a significant fraction of the total population. This is because some of the AGN may be heavy obscured or they can be faint. And so in order to discover the total population of AGN, we need to rely on a multi-wavelength approach in order to investigate the intrinsic emission from the AGN and to reveal. And when, for instance, there is a heavy obscuration, maybe we are looking at the AGN through the obscuring torus, and so we need to use the observation in the X-rays, especially in the hard X-ray band above 10 keV, because X-ray photons are able to penetrate large column density of obscuring material, and so we are able to reveal the primary AGN emission. Or we can use the observation in the mid-infrared, because the primary AGN emission, the one arising from the accretion disk, may be reprocessed by the dust and re-emitted. And so in the mid-infrared, we can look at several features that can be associated with the presence of an obscured AGN. In this context, I performed my work during my PhD in Bologna with Cristian Vignali, Francesca Pozzi, Carlotta Cruppioni, Stefano Marchesi, and many others. And we focused on a finally selected sample of mid-infrared selected Seyfert 2 galaxies. Those galaxies are drawn from the 12-micron galaxy sample, which is an almost unbiased sample of AGN selected in the mid-infrared. These are local objects which benefit from an extensive coverage in terms of observation from the X-rays to the radio frequencies. They have been selected as optically obscured objects, and they benefit from the SED decomposition by previous work from our collaboration. They also have mid-infrared spectra observed with Spitzer IRS. And I focused on the X-ray observation, and we obtain a complete coverage of the hard X-ray band with the NuSTAR, which is essential, as I will show you in the next slides, because only in the case of heavy obscuration, only the photons above 10 keV can be visible. Okay. This is a sketch in order to show how the primary X-ray emission can be observed when we face a heavy obscuration, and the primary X-ray emission can be observed when it passes through the obscuring torus, and we observe an absorbed power law. Plus, we have more components which arise from the reflection on the surrounding medium, and they are usually they are visible as emission lines and a reflection component. I performed both a phenomenological and physical modeling of the spectra, and in what I'm showing in the next slides, I will focus on the phenomenological modeling, but we have also the physical models, the results from the physical modeling with my torus, and are consistent. As you can see, here are some of the spectra for the 36 objects. Not all the observations are available. Some will arrive in the next year. And as you can see here, this is one of the objects for which we will have new NuSTAR data. And it shows how it's important to have NuSTARs neutral observations, because in this case you have only the data below 10 keV, and here you are not able to interpret this as an emission from the AGN, but it may be also interpreted as an emission coming from the star formation in the galaxy. It can be associated with the host galaxy. The X-ray, the characterization of the X-ray properties allows us to determine the intrinsic X-ray luminosities and the level of obscuration here represented, and we can see that this sample is an homogeneous sample, which is large enough in order to investigate with, in terms of it can be used as a statistical sample. It covers over 3 orders of magnitudes in terms of obscuration and column density. We found also some objects which show very faint X-ray luminosity. This can be due to the fact that they host a very faint AGN, and we can use multi-wavelength observation also to classify the presence of the AGN. And for instance, we can use BPT diagram to classify, to look at these objects, which are listed here. And we can look that a couple of those are like are composite objects. And we can use such kind of diagrams like the Keck diagrams, or here a comparison of the observed intrinsic emission with the one which we are expecting from star-forming galaxies. And so the classification is not consistent with all these plots, but we can add also more classification using other lines, especially in the mid-infrared. We also investigate how the obscuration that we measure in the X-ray can correlate with the obscuration that can be observed in the mid-infrared, in particular the one which can be derived by the silicate absorption feature at 9.7 micron. And here we can see that the silicate absorption feature at 9.7 micron, its strength, which is proportional to the ratio of the flux at the absorption feature, correlate for a large part of the sample with the column density derived from the X-ray analysis. But there are many objects for which we see a very deep absorption feature, and this is likely due to a contribution from the host galaxies. And as we can see, and as already been observed in previous literature works, the host galaxy can contribute to the absorption feature in the case of merger or edge-on galaxies. So this means that we need to pay attention when we correlate when we try to compare the obscuration in different bands, because we may have a contribution from those galaxies. A way to avoid this problem could be to model the SED of the galaxies, and in this case, if we used the strength of the absorption at 9.7 micron from the model, we plot this and we derive the associated column density. And what we can see here is that there is a correlation, but of course we have a lot of scatter, because some objects are likely have a not so reliable fit, because also this is also due to the fact that during the SED fitting we have not available a continuous option for the strength of the absorption feature, but we are only using a discrete distribution of the absorption feature strength. And so maybe these are a lower limit of the column density in the mid-infrared, while this maybe is likely some object which has not been which need to have a new fit. And so to conclude this part, what we see here is that the X-ray analysis is very important in order to investigate the intrinsic power of the AGN, but if we need to, there is likely it's likely that there is a correlation between the obscuration in the mid-infrared and in the X-rays, but we need to further investigate in terms of the obscuration, or in terms of the SED fitting using a more defined model. As a parallel work which I've done is to use the same sample to investigate if such a homogeneously defined sample of AGN show some difference in terms of the molecular gas properties with respect to star-forming galaxies in the local universe. And because what is thought is that the AGN is able to regulate the star formation in the galaxies by injecting energy in the interstellar medium and suppressing or enhancing the star formation. And so we compare the molecular gas properties for this sample using new and archival single-dish spectroscopic data to derive the molecular gas masses in the sample of in AGN and in a control sample of star-forming galaxies. And what we found is that there is no significant difference in terms of the molecular gas content between AGN and star-forming galaxies. And also, we do not find the reduced depletion times in the local AGN with respect to star-forming galaxies, as has been observed in high redshift quasars. And so I conclude here, and thank you for your attention.
Okay, questions for Francesco? I have a very naive one. I may have missed that actually, but so what can you learn from these about the selection strategies at high redshift for this obscuration for?
Well, by investigating the fraction of Compton thick AGN in the local universe, we can extrapolate and we can estimate the fraction of Compton thick AGN at high redshift. Of course, this we need to extend also the sample in order to cover a large, in order to have a.
Okay, no, I mean something like, in selection technique, if you can apply something.
Of course, these are mid-infrared selected galaxies. So what we can learn here is about galaxies which are high emitting in the infrared.
Okay. Other question for Francesco? No. Okay. Thanks again. The next talk is by Ivano Saccheo, mean SED of hyper-luminous QSOs.
Good afternoon, everyone. I'm Ivano Saccheo, first year PhD student from the University of Roma Tre, and today I will talk about the characterization of the mean spectral energy distribution of hyperluminous quasars. Now, also already said yesterday by Giustina Vietri, the sample I studied, the YSDSS selected sample, is composed by 85 type 1 radio-quiet hyperluminous quasars with a redshift distribution between 2 and 4.5, and volumetric luminosity is larger than 10 to the 47 erg per second. For this sample, we have quite an extensive photometric coverage, extending from the X-ray region up to the sub-millimeter. And now the most important question: why is it important to study the mean SED of these hyperluminous quasars? Indeed, in the literature, there are already several works which provide excellent description of the mean SED of the bulk of the population, of the bulk of the quasar population. But the problem, these results describe the emission of quasars which have luminosity 1 or even 2 orders of magnitudes smaller than our sources. So we aim to characterize the broadband emission of quasars at the bright tip of the luminosity function with the main goal of investigating whether these extremely luminous sources show intrinsic different properties with respect of less bright sources. And here I give you some, I briefly summarize the steps we took in the derivation of the mean SED, which mostly deal with the attempts to recover the true emission by quasars, which is indeed contaminated by several contaminants which do not allow to gain the real emission by the quasars. In detail, we try to reconstruct the real emission by accounting for the correcting for the intergalactic medium absorption for both the emission lines and the absorption lines in the attempts to recover the true continuum emissions. And we also removed the photometry, which was too much extincted by dust. And we also estimate the contribution by the host galaxy, but luckily in our case, we found that it is almost negligible, since our quasars are so luminous that they almost completely outshine their host. And here's just an example of the magnitudes before and after the corrections were applied for these contaminating factors. And here's the result of our mean SED, which stands for roughly 7 orders of magnitude in wavelengths. And most important thing is here's the comparison with the mean SED by Kravchik and collaborators, which provided the most robust characterization of the spectral energy distribution for type 1 quasars. And I also included their mean SED derived for the luminous subsample. Overall, the shape of these three SEDs is quite similar. Obviously, our SED shows a lower X-ray emission, since our quasars do follow the LX-LUV relation, although with quite some large spread. There are also minor differences in the optical band, where luminous quasars, both from us and from Kravchik, do show a steeper continuum, but the most important difference we found is in the near, and I think it stopped working.
Okay, sorry for this inconvenience that occurs every couple of hours. Okay, maybe now it works.
No, maybe I have to point to no. Okay.
Maybe. Okay.
No.
You get an extra minute.
Maybe I should click slowly. Okay. The main difference we found is in the near and mid-infrared, where we found an extra enhanced emission, which is due to extra dust, an extra dust component. And to further investigate in this direction, we try to model our mean SED by adding a black body to the mean SED by Kravchik in order to investigate the temperature distribution of the dust responsible for this enhanced emission. And we found that the temperature of this dust is between 400 and 700 Kelvin, and it can well reproduce the extra bump that we found between 2 micron and 10 micron. But as we can see, it fails in reproducing the extreme near infrared between 1 micron and 2 microns, where we also see that our mean SED shows a dip between the emission by the accretion disk and the emission by the dusty torus, which is slightly blue shifted to shorter wavelengths. So we added another component, another dust component, and we found that we need an extra dust component with higher temperatures, temperatures larger than 1000 kelvins, which is quite interesting since it is compatible with dust composed by graphite only, since silicates would be likely above their sublimation temperature, and this component must be probably likely be located in the innermost region of the torus, or even in clouds between the accretion disk and the torus. To further investigate this extra emission in the far infrared, we compute the bolometric corrections at the 3 micron wavelength, and I also included the data from the SDSS 10th data release. Now, the first thing to notice is that our quasars do have a lower bolometric correction with respect to the bulk of the AGN population. This is expected since, as we have seen, they have an enhanced infrared emissions. And we also notice that there is quite some large spread in these bolometric corrections. And also that there seems to be a dependence on the bolometric luminosity for the bolometric corrections. In detail, we observe an increasing trend of the value of the bolometric correction up to luminosities of nearly 10 to the 47 erg per second, followed by a flatter or even a slightly decreasing trend for luminosities above. The increasing trend is expected since it is an agreement with the receding torus model, which states that as the primary emission increases, it exerts more radiation pressure on the torus, pushing it farther away and thus decreasing its covering factor. And while the decrease at higher luminosities maybe could suggest that after a certain limiting radius, there is a value beyond which, for an increase in direct emission, it does not correspond a further receding of the torus, but maybe just a heating of of more dust. And just to make another example, here instead I plot the optical bolometric correction, which are known to be constant over several orders of magnitudes in luminosities. And in this case, we see that which quasars, our sample, do follow the same distribution of the other quasars, and we can say that the optical bolometric correction has a constant value of about 4.55 for, I'd say, 4 or 5 order of magnitudes of bolometric luminosities. Now, we also derived the mean SCDs by splitting our samples in 2 subsamples, depending on whether our quasars do show broad absorption lines in their spectra and those who don't. And here's the SCDs we recovered. We see that they are quite different. In detail, bulk quasars do show a lower X-ray emission, which seems to be intrinsic since we used absorption corrected X-ray luminosities. We also see that they have a less steep optical continuum, which is compatible with absorption by dust. And most importantly, they have a steeper near-infrared slope, which is compatible with a more emission by hot dust, which can be located in several different places, from clouds above the accretion disk, or there's even the possibility that this dust could be inside the ball wind itself. Finally, I want to show this diagram proposed by a recent work by Simeonis and Page, and it tries to answer the question, what powers the far infrared emission in active galaxies, which is usually assumed to arise from cold dust located on the galactic scale, which is heated by both newborn stars and the central AGN. But it's sometimes difficult to disentangle these two contributions. So they created this diagram, redshift versus infrared luminosities, and based on the ratio between the AGN and galaxy luminosity functions, they partitioned it into 3 regions: a star-forming dominated region, a transition region, and an AGN dominated region. And they filled this diagram with sources from among the catalogs, which claims to contain the most luminous quasars for a given redshift bin. We included in this diagram our sources, and we see that there is a good agreement up to redshift 3.5. I mean, we know that our sources are most likely IGN dominated, since they are so luminous, but for higher redshift, most of our sources are located in the star-forming dominated. So we propose a slightly different partition of this diagram in order to include also our sources in at least the transition region. But apart from the exact values of this region, I think that the take-home message is that when we deal with such high luminosities, we cannot expect to neglect the contribution by AGN and recover star formation rates by simply multiplying the infrared luminosity for a constant factor, since we will obtain completely unphysical star formation rates. Okay, I leave you with my conclusion, and thank you for your attention.
Thanks. So questions for Ivano? Roberto, here. We have a question here.
Nice work, Ivano. So I was wondering whether you tried, for instance, to divide the sample in redshift bins and check whether there is any evolution of the torus component, so the torus covering factor with redshift.
Okay. We didn't try, actually. It was suggested by several people, so maybe
maybe we'll do it.
We should, maybe.
Thanks.
Another very quick question. If not, I think we can move on. We are a little bit late. Thanks again, Ivano. And the next talk is by Alice De Conto Machado, the main sequence of quasars at high redshift.
Hi, everyone. My name is Alice. I'm a PhD student, a third-year PhD student at Instituto de Astrofísica de Andalucía in Granada, Spain, and under the supervision of Dr. Ascensión del Olmo and Dr. Paola Marziani. And during my thesis, I'm dedicated on investigating the behavior of high redshift and high luminosity quasars under the context of the main sequence of quasars. So the talk I prepared for today is directly related to that and is entitled The Main Sequence of Quasars at High Redshift. So here is an outline of what I'm going to say. And I know that you have already heard, at least in this conference, about the four-dimensional eigenvector 1. But I think that it's worth to recap this. So in the early 2000s, it has been proposed by Sulentit and collaborators, the four-dimensional eigenvector 1, which I will call from now on the 4DE1. And basically, we can set the 4 basic parameters for the 4DE1, which are the full width of the half maximum of Brock component of H beta, the RFE, which is the ratio between the intensity of the iron 2 and the H beta, the blue shifts of high emission lines such as carbon 4, and the soft X-ray photon index. The main sequence of quasars consists exactly on the optical plane of the 4DE1, and this shown in this, in this plot over there. And basically, the main drivers of the main sequence of quasars are thought to be the Eddington ratio and the orientation. And in this sense, we can separate the sources into population A and population B, as you can see here, considering also the full width half maximum of H beta and also the RFE, which is the intensity. So usually population A are the ones that present high Eddington ratio and the strongest outflows. And when we go to the population B domain of the main sequence is where we found sources with low Eddington ratio. So, no, it's not this. Here. So, okay, if you go to see in the literature, the main sequences have been initially and widely studied in low redshift data, usually lower than 1, on average 0.8 or so. So, on the other hand, when we go to the high redshift context, the main sequence of quasar need to be more explored. So, in light of this, we are developing my thesis. From until now, we have already studied 22 sources, and here's a comparison of our sources in pink, and in gray we have the data release 16 of this one. So you can see that in general.
You can see actually, but sorry about that. Thanks, Emmanuel. Please, sorry.
Okay, so now, yes, you can see that on average our sources present a higher redshift and a higher luminosity when compared to the average of this LOAN data. And the main, okay.
You get an extra minute, of course.
Okay,
well.
Thank you. Here. So, in light of the analysis of these 22 sources, we have developed this paper, which has been already submitted to the ANA. And my talk from now on will be focused on the results that we are showing this paper. So the data we are using is basically optical and UV. In the optical, we have used observations from the infrared of VLT. And for the UV, we are using archival data, mainly ISLOAN again. So in order to analyze our data, we are performing a nonlinear multi-component fitting using the IRF spec fit task. And with this, we are able to represent the profile into 4 different components, depending if it is broad profile or not. So in all cases, we have a broad component, which is the BC. Blue, usually found in population A, but when we go to high redshift, as I will show you, we also find this in population B. Then the VBC, which is also only found in population B, and then the narrow component, which we use to determine also the redshift. So I forgot to mention, here is for the optical. So blue is population A, red population B. And similar analysis was also performed for the UV. So we have silicon 4, carbon 4, and the 1900 blend. Once we have that, we can determine the properties of the full profile. So we have the full width, the intensity, the kurtosis, asymmetry indexes, and centroid shifts, which will be very important for our analysis. Once we have that, we can locate our sample in the main sequence. So if you see here in this plot, which is similar as the first one I show you, the gray area and the green one indicates the main sequence at low redshift. So you can see that we have here the population A that are above the limit that we found for population A in low redshift. So we can conclude that usually when we go to a high redshift context, the main sequence kind of shift towards a higher full width of H beta. And this is an effect that has been seen not only in our sample, but also in other high redshift samples. Okay, and then we also perform this plot, which consists of the full width of the full profile of H beta and the BC. And here is the one-to-one line. You can see that population A in general present almost one-to-one. But when we go to population B sources, you can see that they are not represented fully by the BC, and they need at least a VBC, which is usually very broad. And as you can see in this plot, which indicates the shift, the VBC is needed and is very shifted to the red and represent more or less 50% of the full profile and is very, very broad. On the other hand, it's not this. This plot also shows that at least in extreme A's, which are represented by the magenta colors, and also in some other population A, we find outflows not only in oxygen 3, but also in H beta. And since I start talking about oxygen 3, here is a comparison between the full profiles of H beta and oxygen 3. And usually the population A that are the ones that present usually a higher Eddington ratio presents in some cases values of full width of oxygen 3 that are comparable to those that we found for H beta. And this is not exactly true for population B sources. Here we have a comparison between the shift of oxygen 3 and the full profile of the full width of the full profile. So you can see that sources that present the broadest profiles are also the ones that are more shifted towards the blue. And this happens especially in a high Eddington ratio. However, here we have a comparison sample and in open squares, and they are also population A in blue and population B in red. And you can see that, okay, we do find outflows in population A, but when we are dealing with high redshift sources, we also find outflows in population B ones. However, the profiles of oxygen 3, when we go to a high redshift context, used to be very broad and irregular. So we should not rely on oxygen 3 when we are determining the redshift in the high redshift context. Due to this fact, since we cannot determine exactly where is the narrow component, then we cannot take the oxygen 3 for serious. Okay, and if you remember, I have made this plot for oxygen 3, and then we decided, what about carbon 4? And we did, since we have UV, we also did this plot, and we found that sources that present strong shifts in oxygen 3 will also present it in carbon 4, and especially the sources that are more the sources that are extreme A's, such as this magenta, these 3 ones, are the ones that present more shift. More shift in carbon 4. Okay. Similar. Here we have then put carbon 4 and oxygen 3 together with the shifts, and we found a correlation. And this may indicate that this kind of indicates a physical connection between inner outflows represented by the carbon 4 here in this plot and outer outflows represented by oxygen 3. Apart from that, we have also estimated black hole masses using not only Ag beta, but also carbon-4 and aluminium-3. And since we have the black hole masses and the luminosity, and the additon ratio, we tried to make this plot on the left here, which is the equivalent width of oxygen-3, the full profile, and the peak shift of the profile of oxygen-3. And in gray and yellow, we have low population A and population B, low redshift population A, population B. And here we have high redshift sources in blue and red. What we found is that when we select sources that present a peak shift larger than 250 kilometers per second, what we find is that they are located in a very small range of equivalent width, usually lower than 25 angstroms, and they are found in all range of black hole masses, but they are only found in sources that present high additon ratio, and especially sources at high redshift in this context. And here is my summary, and thank you very much for your attention.
Thanks, Alice. Questions for Alice? Okay, sorry. We have
So I'll move back to the slide I wanted to.
Good that you can go by yourself.
I can do it. Okay, so here you see that the population A not only moves upwards because H beta is broader, but also to the left, which is probably the same effect.
Yes.
But do you think also evolution of iron templates or the abundance of iron at high redshift affects this behavior?
Yes, because actually this is a discussion that is very hot right now in this topic. And the iron 2, yes, could be a cause of this. And especially because if you see sources that are more extreme A's, that are located as A3 and A4, they are, in some cases we do not find iron 2. But when we go to sources that are at higher redshift, then yes, we can find it. But yes, could be.
One last question there.
Yes. So you have found full width at a maximum of oxygen-3 up to 5,000 kilometers per second.
In some cases, yes.
Are you sure that's not iron? Because you know that there is an iron multiplet right next to the oxygen-3, so...
Yes, but in these sources, they are very... there are only 2 or 3 that happens this effect. And in these cases, it's true that we cannot determine exactly which is the components that we have in oxygen-3, but we can, yes, determine well the iron 2 template that we are using. So the iron 2 is very well established, but we are not very sure about the oxygen-3, so it could be, yes.
Okay, thanks again, Alice. And now, Alessandro Paggi. So now we have Alessandro Paggi with the X-ray surveying radio-loud AGNs and their large-scale environments. First results from B2CAT.
Okay, hello everybody. Thanks for giving me the chance to present you this talk, in which I will show you some preliminary results that me and all these collaborators listed here from all these institutions listed here are collecting from this Chandra snapshot survey on the second Bologna catalog of radio sources. So, first of all, X-ray from radio galaxies have been observed in a number of sources on scales of hundreds of kiloparsecs, and they are usually associated with one of the following processes, like, for example, synchrotron-Compton that usually dominates in radio hotspots, or inverse Compton on the cosmic microwave background, usually more prevalent when the X-ray structures appear to be aligned or morphologically consistent with the radio emission. Inverse Compton from far infrared photons in galactic starburst, and lastly, thermal emission from the hot gas intergalactic medium when this source happens to be hosted in a group or cluster of galaxies. In order to extend the multi-wavelength coverage of the third Cambridge catalog, in 2007 we started an X-ray snapshot survey, meaning that we requested short observation, shorter than 20 kiloseconds, with Chandra, in order to acquire X-ray data with an angular resolution that could be compatible or comparable with the one that we have in the optical and radio band. So far, we acquired data for more than 100 sources, providing flux images and flux maps in at least 3 energy bands, and basic parameters like counts, net counts, and fluxes for nuclei and other radio structure detected in the X-rays, like lobes and knots, hotspots, and so on and so forth, and also performing X-ray spectral analysis for the brightest nuclei and X-ray detected structures. Although these observations are very, very short, I want to emphasize what is the power of the snapshot, because of this kind of snapshot survey, because they provided very interesting results, being able to detect an extended emission in sources like this one, 3C89, or being able to detect X-ray emission from radio hotspot in a number of sources like 3C313, and the radio emission associated with radio lobes, like this one, and even in radio knots, like in the case of 3C17. Yes, okay. One very nice example of an interesting sources that have been studied with the Chandra data collected during the snapshot survey is 3C196.1 that in an analysis performed by Federica Ricci in 2018 showed an inner cavity in the Chandra data that is probably linked with a past merger event, so due to sloshing in the X-ray gas, and also an outer cavity at the larger radii that is probably linked to the central AGN outburst. If you want to know more about this source, I strongly invite you to take a look at Anna poster that you can find outside in the coffee break area. So another catalog that is of a radio source that is used for studying radio-loud galaxies is the second Bologna catalog that lists about 10,000 sources detected at 408 megahertz with the Bologna Northern Cross telescope. And since it is a low radio frequency selected sample, it is unbiased toward the X-ray emission and AGN orientation. It also covers a wide range in redshift and radio powers, and is also augmented by a vast suite of multi-wavelength observation, both space and ground-based, and also by an extensive imaging observation in the radio bands at other frequencies. And therefore, it represents an ideal sample to investigate the properties of active galaxies. To this end, in 2018, we submitted a white paper for the Chandra Cool Target programs, adopting a snapshot survey similar to the one that we used for the Cambridge catalog, that is requesting observation for a list of more than 1,000 sources with an average snapshot exposure of 16 kiloseconds, and also we collected the radio imaging data from various radio survey like the VLSSR, LOFAR, TGSS, MVSS, and VLASS. The main goal of this program is again to study the X-ray emission arising from the radio structure like jet, nodes, hotspot, and nuclei of these radio sources, and searching evidences of IgN interaction with the surrounding gas, and also with the goal of finding galaxy clusters or groups through the detection of the extended array emission not associated with radio structures. So far, it's extremely sensitive. Okay, so to date we got in the last months observation for the first 19 sources of this program, and I'm going to show you some preliminary results. So first of all, we were able to detect nuclear emission in 15 out of these 19 sources. In all these pictures, you can find on the left panel the soft band Chandra image with overlaid the LOFAR contours, while on the right is the same image but in the full band 0327 keV, with overlaid in white the TGSS contours and in green the VLA contours. So as you can see, in many cases you see the nucleus both in the soft and in the full band. In some cases you only find the nucleus detected in the full band due to its harder emission and to the decreased effective area of the instrument. We were able to extract nuclear spectra from 3 of these sources, and we fitted them with a simple power law model plus galaxy absorption, excluding the pixel of pile up larger than 10%, and we found these slopes 1.6 to 2 that are very reasonable slopes for nuclear emission of AGNs. We also found extended emission in 3 sources. We found it by comparing the surface brightness profile of these sources with a simulated PSF at the position of the nucleus. And in these cases, we found that the surface brightness profile clearly extends above the level of the PSF. These are the 3 sources for which we found extended emission. In these cases, we see that the extended emission appears to be more or less correlated with the radio emission, while in this case we see that the extended emission extends much beyond the structure that we see in the radio band. We were able to extract the spectra of this extended emission for all these 3 sources, finding a temperature of about 4 keV. In particular, for these 2 sources, we were able also to estimate the luminosity because we have the redshift estimate. And so we put them on this plot where you can find the X-ray luminosity versus the temperature of the gas. Those are the 2 sources that for which we have the redshift estimate. And we can see that they show temperatures that are more similar to the one that we found in clusters, indicated with the triangles, rather than the one that we see in groups, indicated with circles. And however, the gas mass that we can estimate for these sources is the order of 10 to the 12 solar masses, which is a value that is more similar to the one that we observe in groups. In particular, this source appears to be hotter, to have hotter gas with respect to its X-ray luminosity. As a matter of fact, if we take a closer look at this source, we see that it has a very complex and disturbed X-ray morphology. Also, the radiomorphology that we see in with LOFAR data shows this wide-angle tail morphology with this dramatically bent jet. We also find a marginal indication, the presence of 3 cavities in the X-ray emission, indicated here with white circles, although the detection of these cavities is marginal because it attains at a 3.5 sigma significance. So those are the conclusions. We found, we got observation so far for 19 B2 sources. We were able to extract, to detect the nuclear emission in 15 of these and to extract nuclear spectra in 3 of them. And also we found extended X-ray emission in at least 3 of them. There are also hints of the presence of X-ray detection of hotspots in at least 4 sources, but I'm still working on that. And also we plan to augment this data with mid-infrared imaging from WISE and optical imaging and spectroscopy with PAN-STARRS and SDSS. So the takeaway point that I want you to take home is that I hope that I convinced you of the power of the Chandra Snapshot Survey program. This kind of observation are able to yield a very interesting result despite their short exposure and despite the decreasing effective area of the instrument. And that's it. Thank you.
Thanks, Alessandro. Questions for Alessandro?
So how many counts do you have in the source where you can get the spectra?
Okay, I don't have the number on top of my head, but you mean the nuclear spectra? Yeah. Well, you can see this is binned for 20 counts per bin, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, so 200.
The other dozen or so are very faint? Or?
Okay, so there is, let me see if I have it. Maybe I can show you. So, yes, there was also this one, but as you can see, due to the effective area of Chandra that is not as good as it used to be, below 2 keV, we have absolutely no counts there, and so the slope is not constrained at all, and so you get values of 3 that are unphysical, unless something very weird is going on there. But for all the other sources, probably we will have, okay, this is a collection of all the other sources, and as you can see, even if the nuclei are not bright enough to perform spectral fitting, probably we can do something with counts, and we can assume a model and then evaluate luminosity and fluxes and so on and so forth. So a lot of stuff can be done with this also because there are a lot of different morphologies, FR2, FR1, white stuff that looks like nothing, and so.
I have another question. Going back to the diffuse emission.
The diffuse emission.
I haven't understand. You try to remove the emission along the radio emission?
So you mean extracting...
So those temperatures are from all the diffuse emission?
Yes, and so you mean...
So you take it, there is a non-thermal component.
Okay, this kind of study I didn't do yet for this kind of source. We did it for other sources that we found with in the 3C catalog, like for example this one. Dov'è che sta? Ecco qua. Like for example, in this case, this is exactly the work that we did. We tried to disentangle and separate the thermal emission from the non-thermal emission, at least in the, let's say, the cone direction along the radio jet and the cross-cone direction, and also using multi-wavelength data like the one that we collected for this survey. So you are able to model the multi-wavelength emission and make predictions on what you would expect about the slope of the emission in the lobes or in the knots or in the extended emission, basing on different the models, like for example a non-thermal model like the SSC or the ICCMB, and then you can constrain. Of course, probably you need much more counts to.
But in the snapshot, so in the snapshot you leave with the contamination from the non-thermal component.
A little bit. But for example, in this case, we were able to say that at least in the lobes, the non-thermal component should be dominant. We were able to disentangle it, while in the cross-cone direction, the thermal is dominant. So maybe there is also a cluster there. Who knows?
Sure. Okay. There are no other questions. I think we can thanks again, Alessandro, and move to the poster presentation. Now there is a little change. So I read the order. The first one is now Ilaria Ruffa, then Alba Vega Alonso Tetia, Matthew Thorne, Olena Torbaniuk, Tommaso Zana, and Francesco Zivaro. I don't know about the accent, but so you can start whenever you want.
2 minutes sharp, I'll be ruthless.
He is actually ruthless.
Volevo fare il pointing, ma non capisco. Okay. So, good afternoon, everyone. I'm Ilaria Ruffa, and I work as a postdoc at Cardiff University. In this poster, I present a multi-wavelength study of the jet-ISM interaction in the low excitation radio galaxy NZC 3100, hosting young radio jets. We carried out this study using ALMA observations of multiple molecular gas transitions, plus high-resolution JVLA observations at 10 gigahertz. And as you can see, we nicely detected CO120, 221, and 322 transitions, showing the presence of a main central rotating CO distribution extending up to 2 kiloparsec, plus some patchy structures on larger scales. We also made the CO lane ratios and carried out detailed kinematic modeling, indicating higher gas excitation in the central regions, plus a mild outflow on the CO kinematic minor axis. And by making a spatial comparison with the radio jets, we conclude that these features are jet-induced. But why this is important? Mainly because it is relatively new, the finding that radio jets can have a huge impact on the galactic gaseous reservoirs on sub-kiloparsec scales. But most of the studies carried out so far were mainly focused on nearby Seyfert galaxies. So this is the first detailed study of this kind using multiple molecular lines in a low excitation radio galaxy, making 3100 the archetypal example for jet ISM interactions in this kind of objects. And if you want to know more, please come to me.
Thanks.
There is a fight in the AGN community. Half of the people follow the evolutionary model, thinking that the galaxies, the obscuration of the AGNs, depend on in what moment of their history we are observing them. The other half of the community prefers the orientational model or the unification model, where the obscuration of the AGN depends on what is the position with respect with the observer. And the community is divided. Half of the scientists use one, the other half use the other. I'm different. I'm Alba. I studied with Francesco Shankar in the University of Southampton, and I am part of the B4BSTN, one of these groups that there has been a few of us are here. And my grant is under the Marie Curie Fellowship. And in this project, I work with Fabio Fontanot in the audience and Nicola Menci. And my job is to find the key variables that defines the AGN obscuration to find why that obscuration comes from and which one of the models is better. So if you want to know what I found, go and read the poster. So thank you so much.
Ciao, my name is Matthew Thorne. I'm from Lancaster University and I work with Dr. Brooke Simmons. I'll be talking about the growth of black holes in the merger-free galaxy regime. In recent years, observations and simulations have suggested that black hole growth, unrelated to the processes from galaxy mergers, is actually the driving mechanism for black hole growth. However, not all studies agree. We have taken 3 such studies from samples, and they are the the Simmons samples, the Bernard samples, and the Rainey samples. And we have plotted them here for their black hole mass and their stellar mass. And they disagree on whether disk-dominated galaxies follow the black hole stellar mass relation. One thing they do all agree on is the top right corner, that the bolometric luminosity, which is essentially the black hole growth rate, is the main indicator to whether they will fall on the black hole stellar mass relation. So we also wanted to unify these 3 samples into one coherent picture. So we produced a simulation where we grew black holes based on correlations between black hole duty cycle and Eddington ratio, and then used a X-ray selection function to produce a sample of unobscured AGN. And then using a selection function based on flux and redshift derived from each sample, we selected it and reproduced the properties from those samples. The mass and luminosity is shown up there, and they are all in relatively good fit. So this suggests that they were all drawn from the same underlying population of supermassive black holes, and that selection effects are really important to consider. If you have any questions, come talk to me or send me an email, and thank you for listening.
Hello, everyone. My name is Elena Tormanyuk. Probably you remember me from my Monday talk. So today I want to present you also my poster. So it's about improved technique for quasar continuum prediction in the Lyman alpha forest. So we all know that Lyman alpha forest is a set of absorption line which was created by absorption of quasar light by nitrile hydrogen in intergalactic medium. So we have this set of lines. And we know that Lyman alpha region is a perfect tracer for study the intergalactic medium because we have all this absorption line. But there is a huge problem. So if you want to study the intergalactic medium using this Lyman alpha region, you need to restore the intrinsic continuum of quasar before this absorption. And there is a huge problem because there are a lot of different methods how to do it, but one of the best one is to use a composite spectra of the same quasars. But all people who previously used a composite spectra, they do like, we have this sample of quasars, we just edit, create one of several composite spectra, and we use it. But we forget that each, even if we know that from one object to another, quasars in general similar, they are still different in case of slopes or luminosity and other stuff. And it's a fact, actually. So in my work, I just created composite spectra using different subsamples of quasar spectra, and each subsample has a different slope of this spectra, or they have they have different luminosity. So in the result, I obtained like 92 composite spectra, which is this one, which is absolutely different in the luminosity and spectral indices. Here I present a couple of them, so another one on poster I can show you. And I applied all these composite spectra just to individual spectra of quasar to find the continuum in Lyman alpha region. So I just tried to find the reliable and appropriate composite spectra for each individual. Okay, for each individual. Yes, for each individual one. So I just now have used in the composite that I have continuum from 40,000 individual quasar spectra. So if you're interested in this, my poster upstairs, so you can find me and discuss this. Thank you.
The model, this toy model, in order to compute which is the total energy which hit a single galaxy. You can see the galaxy in the top right corner, and that's just
actually, I wanted to answer to the question, which is the effect of EGN feedback at high redshift on the environment of the host galaxy beyond the viral radius of the galaxy, and in particular on the satellites. And I did this through the use of numerical hydrodynamical simulation. And in particular, what I did is to develop this model, this toy model, in order to compute which is the total energy which hit a single galaxy. You can see the galaxy in the top right corner. And that's just a schematic representation. You have the AGN in the little galaxy in the... Yeah, you got it. And so when you get this energy and you plot its evolution and you compare it with other properties of the galaxy, these, for instance, are just two galaxies around the central quasar. It is very interesting. You can see that the timing is remarkable, and it seems that you have, for instance, in this case, a positive effect on the star formation, on the satellites around the high redshift quasars. And it seems this is due to the energy which is directly coming from the AGN. And this has obviously some very interesting consequences, such as on the evolution of the satellites or on our capability to observe them, and also to infer, for instance, overdensities of objects around these quasars. So I think this is pretty much everything. Obviously, it is much more complex than this. If I succeeded in intriguing you and you want to have a chat on this, let me know. I'll be around. Thanks.
Hello, everyone. I'm Francesco Ziparo, currently working on PBH accretion at Scuola Normale under the supervision of Simona Gallerani and Andrea Ferrara. So, motivated by incoherences between the theory and observation for the X-ray and radio background, we ask ourselves, can a population of primordial black holes accreting at high redshift explain the excess observed in both bands? So, as you heard this morning, primordial black holes are black holes formed in the very early universe, but also a dark matter candidate. Under the assumption that a fraction of dark matter, FPBH, is composed by primordial black holes, we developed a semi-analytical model to describe primordial black holes accretion and their contribution to cosmological backgrounds. On the left, you can see a toy model or an illustrative cartoon of this model. So at any given redshift, PBHs are distributed following the dark matter density distribution. So part of them lies into the IgM, where the gas is underdense, and part of them sits inside HALOS. And there, inside HALOS, where the gas is more dense, the accretion and thus the radioluminosity and also the X-ray luminosity is much more efficient. On the right, I'm showing the redshift evolution of the cumulative soft X-ray background redshift evolution. Different colors represent different assumptions on FPBH, while the blue shaded area represents the observed X-ray background excess. As you can see, even a tiny fraction of the order of 10 to the minus 4 of dark matter into primordial black hole might explain the observed excess. So if by now you're asking yourself, what is a primordial black hole guy doing in an AGN conference? you should ask me tomorrow at the coffee break. Thank you.
Thanks again. So I'd like to thank all the speakers of this morning also for being in time. And tomorrow we have the session on feeding and feedback. And of course we have the concluding remarks. So see you tomorrow at 9. We convene at 9 a.m. and have a good evening.